So in this video, we're going to develop the parametric form of the Arclength formula. So remember in a previous video, we developed the formula for Arclength. We had a couple different ways of looking at it. We're going to focus on using this one. And what we want to do is identify that if we parameterized our curve, so we have x of t and y of t, then for this this number a right here, right, x is running over the interval from a to b, there's going to be some t that generated that a, we'll call that t sub 1, and b, we'll say, hey, x of t sub 2 equals b. There's going to be a value t sub 1 and t sub 2 that when plugged in for x generate the a and b. So when x runs over the interval from a to b, if we've parameterized a curve, we're going to find that t is running over some interval from t sub 1 to t sub 2. And what we can do is manipulate this formula for arc length that we already derived. We can manipulate it into a form that is amenable to parametrically defined curves. So here's the idea. We're going to do exactly what we said on the previous slide. We're going to say, hey, x is running over the interval from a to b, and we're interested in finding the arc length of the curve over that x interval. But as x is running over the interval from a to b, t, if we have a parametrically defined curve, is going to be running over the interval from t sub 1 to t sub 2. So we're going to take our parametrically defined curve, x of t equals some f of t, and y of t equals some g of t. So if we had the rectangular form, we would say, hey, run over the interval from a to b and take the square root of 1 plus f prime of x squared dx. And we want to remember that f prime of x is just another way of saying dy dx. These statements are synonyms, and we already noticed that we can calculate f prime of x if we have a parametrically defined curve by noting that dy dx is just equal to d dt of your y of t divided by d dt of your x of t. So if we do some side work, the stuff under the square root sign here, let's say we do some side work. We say, hey, I have 1 plus f prime of t, and I want, f prime of x, and it's squared. I could rewrite this using the parametric form of the derivative as dy dt, which is the y prime that goes in the numerator over dx dt, and this whole quantity would be squared because dy dt divided by dx dt is dy dx, or f prime of x. And if we're squaring a numerator and a denominator, we can square the numerator and denominator separately. And here we're supposed to add 1 to the derivative, but 1 can be written in all kinds of interesting ways. So let's write it in terms of this denominator here so that we have a common denominator. So I'm going to write dx dt squared over dx dt squared, which is just another way of writing a 1. If I do this, now I have a common denominator. My common denominator is my dx dt, which is being squared, and here I have dx, I'm going to have dx dt squared plus dy dt squared in the numerator. And so notationally, just to make this a little easier to write, let's just write this in the prime notation. So dx dt is in prime notation x prime of t, which is being squared, and dy dt can be written as y prime of t, which is being squared. And let's take this mess now and dump it under our radical sign. So we're working on the interval from a to b of the square root, and here we have x prime of t being squared plus y prime of t being squared, and this is all over. We have a dx dt being squared, And then if we look at that carefully, we see that we can simplify it because you can take the square root of the numerator, which is x prime of t quantity squared, plus y prime of t quantity squared, and the square root of the denominator separately. As long as they're not both negative, we can do this, and we know they're not both negative because everything inside of the radical is being squared. And sorry, this should be pulling down a dx all along the way. And then the square root of we'll cancel the squaring right here. So boom, the square root cancels the squaring, and we're left with the dx dt right here. And what we want to remember is that if we are dividing by a ratio, that is the same as multiplying by the reciprocal. So multiply by the reciprocal is the same as dividing. The same trick we use in elementary school when we do 1/2 divided by 3/4, which can also be written as 1/2 divided by 3/4, and then we're taught, we're usually not they don't usually tell us why, but we're taught to change division to multiplication and just multiply by the reciprocal. So taking advantage of that here, and now I have dx sitting here in the numerator position and dx in the denominator position, and those are going to cancel and leave me with an interval that's strictly in terms of dt. And because now my integral is in terms of dt, I want to run it not from a to b, but from t sub 1 to t sub 2. So kind of formalize that on the next slide, something that you can put in your notes. If c is a parametrically defined smooth curve with x equals f of t and y equals g of t, that does not intersect itself on the interval from t sub 1 to t sub 2. The exception would be if it intersects at the endpoints, but in general we want a non-self-intersecting interval. Then here's our arc length calculation. This is square root of the sum of the squares of the derivatives of the parametrically defined function. So it's actually kind of a nifty formula, and I think an easier form to use than the original arc length formula that we had to develop.